Welcome to my YouTube channel, A Binary of Civil.
In this session, I am going to solve the second assignment of reinforced concrete road bridges. This course is only a 4-week course. So you need to submit all the assignments. Okay, are you ready? Let's start. See, first question, a rectangular beam of width 400 mm. So he has given a rectangular beam of width, he has given 400 mm, and overall depth means it is capital D, it is 570 mm, that is from here to here. Okay, M20 grade concrete he has given, and Fe 415 steel. The tensile reinforcement provided by 416 mm dia bars, tensile reinforcement that is provided in tension zone. So these are 416 mm bars. So he has provided 4 bars of diameter 16 mm and the clear cover is 20 mm. So clear cover is 20 mm. So clear cover means it will not include the reinforcement from here, the bottom face of reinforcement to the bottom of beam. This is 20 mm. This is clear cover. Now effective cover is, it will include half of reinforcement. So this is effective cover. Effective cover is equal to clear cover plus dia by 2. Okay, and the remaining depth will become effective depth. So this is small d. Okay, so to calculate effective depth small d, we need to deduct clear cover and half of diameter from capital D. Okay, so you will get capital D minus clear cover minus dia by 2. So capital D is 570, he has given, clear cover 20 minus 16 by 2, you will get it is 542 mm. This is effective depth. This is the way to calculate effective depth, 542. Answer is D for question number 1. Next question, a rectangular beam of width 450 having overall depth 550. So first let me draw the diagram. So this is 450, capital D is equal to 550. So you have to observe very carefully. Sometimes he will give you overall depth, or some other times he will give you only effective depth. So be careful by during taking the observation. And he has given M30 grade concrete and reinforcing steel is Fe 415. The tensile reinforcement provided by, here there are 5 reinforcing bars of diameter 16 mm. The provided area of steel is equal to, so first we will calculate area of steel. Area of steel is AST, that is 5 into pi by 4 16 square, you will get it is 1005 mm square. Okay, area of each bar is equal to pi by 4 16 square. There are 5 bars into 5. So the answer will be C. For question number 2, the answer is C. And now coming to third question, a rectangular beam of width 300 mm having overall depth 550. You can take, this is 300 mm and it is 550. The concrete is M30 grade concrete and steel is Fe 415 steel. The tensile reinforcement provided by 3 number of 20 mm bars. The area of steel in balanced section is, the question is area of steel in balanced section is. Okay, first of all, what is balanced section? When actual depth of neutral axis will be is equal to critical depth of neutral axis, then we say that is x actual is equal to x critical. Okay, for Fe 250 critical depth of neutral axis is 0.289 D. Okay, so these values I have explained in reinforced concrete designs DRCS subject. So what are all the critical depth of neutral axis? So first of all we will calculate small d. So here small d is equal to 550 minus, I am assuming, because to calculate small d we need to have clear cover. Clear cover I am assuming 25 mm. So that is 25 and dia will be 10. So you will get it is 515 as the effective depth. So critical depth of neutral axis will become 2.289 into 515. So you will get it is 148.835 mm. Okay, so this is critical depth of neutral axis. Now he asked us to calculate the reinforcement to be provided so that the section is balanced section. Now to calculate reinforcement, b into xa square divided by 2 is equal to mast d minus xa. So b is 300 and xa and xc both are equal, that is 148.835 whole square divided by 2. And here again one more question, that is small m is equal to modular ratio. Its formula is 280 divided by 3 sigma cbc, that is 280 divided by 3 sigma cbc for M30 grade concrete is 10. Okay, so it is 10. Sigma cbc value is generally 1/3 of grade of concrete. Okay, so you will get m is equal to 9.33. So 9.33 and ast provided is equal to, we need to calculate that I am writing here, it is ast balanced, and d minus xa, d is 515 minus xa is 148.835. so in this entire equation the only unknown is ast. Okay, so you will get it is 970 mm square. So the answer is near to 965. Okay, because we have assumed the clear cover as 25 mm. It might be 30 or 20 or he hasn't provided the data, so that's why I assumed. I got the answer approximately, it is very near to 970 mm square. So the correct answer for this question is option D. So coming to next question, for a rectangular beam, width is 400, overall depth is 550. First let me draw the diagram. So width is 400 and depth is 540 mm. This is overall depth, not effective depth. Reinforcement provided by 12 mm bars. He has not given how many number of bars. Okay, and clear cover is equal to 30 mm. Grade of concrete is equal to M30 and Fe415 steel. Working stress method, that is WSM, the position of neutral axis from compression side in a balanced section is. Okay, obviously for a balanced section, critical depth of neutral axis is equal to 0.289 d, that is for Fe415 grade steel. So to calculate 0.289 d, we need to get d value. D is equal to capital D minus clear cover minus diameter by 2. So that is 540 minus clear cover is 30 and the diameter is 6. So you will get it is 504 mm. So this is small d. So now xc is equal to 0.289 into 504. You will get it is 145.6 mm. So it is very near to 147 mm. Clear? So the answer is A for question number 4. Okay. Next question. The width of rectangular beam is 400 mm and overall depth is 540 mm. So the dimensions are same as earlier problem. So this is 400 mm and 540 mm. So this is capital D. So now he has given Dia of bars is 12 mm. Clear cover is 25 mm. M30 grade concrete. FE4, same story, FE415. As per working stress method WSM, the compressive force in concrete is equal to, generally in working stress method, the stress block is in linear variation. Okay, so here this is sigma CBC, okay, and it is XA. So first of all, we will get a small d value. Small d is equal to 540 minus 25 clear cover minus half of the diameter is 6. You will get it is 509 mm as the effective depth. From this we can calculate XA is equal to XC is equal to 0.289 into 509. Okay, so this is depth of neutral axis. Clear? Now to calculate compressive force, this entire portion is in compression. This what is the area of this entire portion of sigma CBC into XA? To this, inside width has to be added. So that is half sigma CBC into XA into B. So that is half sigma CBC is for M30 grade concrete, sigma CBC is 10, that is 1/3 I already explained, 10, and XA is equal to 0.289 into 509 and width will be 400 mm. So you will get the answer is 294.202 Newton. It will be 294.202 kilonewton. So the answer will be answer C for question number 5. Clear? And question number 6, same question. He asked maximum tensile force. So it is 400, 540 and M30, FE415. So for FE415 sigma ST, that is tensile stress will be 230 Newton per mm square. Okay, so in this diagram, tensile force sigma ST into AST. So as the diagram variation is this much. So this is compressive force, this is tensile force. Tensile force stress into area. So stress will be, and he mentioned that there are 3 bars of 12 mm. Okay, this is AST. So 230 into AST will be 3 into 5 by 4 12 square. So total you will get it is 78037 kilonewton. Sorry, it is only Newton. So it will be 78.037 kilonewton. Clear? So the answer will be D for question number 6. Let's go to next question. So 7th question, a rectangular beam of width 350 and overall depth capital D is equal to 600 mm. The tensile reinforcement provided by, there are 20 mm bars. He has not mentioned how many number of bars. Clear cover is equal to 25 M30 grade concrete, FE415 steel, and the lever arm in the balanced section. First of all, balanced section means XCA is equal to XC is equal to, for FE415 it is 0.289. Okay, I'll explain here what are all these values. So that is 0.40D, 0.289D, 0.254D. These are all critical depth values in working stress method. This is for FE500, this is for FE415, this is for FE250. For us, the given steel is FE415. So I am taking XC is equal to 0.289 D. First of all, we will calculate small d is equal to capital D is 600 mm minus clear cover is 25 and half of the diameter of the bar is 20 by 2. You will get it is 565 mm. So then you will get critical depth of neutral axis is 0.289, d is equal to 565. It will be 163.285 mm. Okay, so as the variation is in the linear portion, so this it is XA and the triangle, this triangle centroid is somewhere here. This distance is XA by 3 and this will become lever arm. T minus XA by 3 will be lever arm. Okay, so I am writing here lever arm. Lever arm D minus XA by 3. So that is, what is D? It is 565 minus 163.285 divided by 3. Okay, so it will be 510 mm. Clear? So this is answer A for question number 7. Okay, and question number 8. The rectangular beam of width 400 mm, 400 and overall depth is equal to 650. The tensile reinforcement provided by 316 mm bars. The clear cover is 25. The concrete is M30 Fe415 steel. As per working stress method, the position of neutral axis from compression side forth provided is equal to, that is, he asked us to calculate the position of neutral axis. So position of neutral axis can be calculated by an equation B into XA whole square by 2 MAST D minus XA. So in this, M is equal to 280 by 3, sigma CBC value is 10, it is 9.33 and B is 400. XA value whole square divided by 2 plus M is equal to 9.33 and area of steel is 3 into pi by 4 16 square and D. So we need to calculate the value of small d, that is capital D minus 25 minus 8. So small d you will get it is 617 mm. Okay, so 617 minus XA. So in this equation the only unknown is XA. So XA is equal to 144.5. This approximately is equal to 145 mm. Okay, so it is 8. Answer D for question number 8. Now there are only 2 questions. Same types of problems. So every rectangle beam is taken, width is given, depth is given. So same story. So in the question number 9, a rectangular beam of width 350 mm and overall depth capital D is equal to 600 mm. The tensile reinforcement provided by 3 bars of 20 mm and clear cover is 25. M30 grade concrete, Fe415 steel. Compressive stress due to bending reached at the compression side for the provided section is equal to, that is, we need to calculate the compressive stress. We have a formula to calculate compressive stress, that is sigma CBC, or we also call it as C suffix A, sigma ST into XA divided by MD minus XA. Okay, so this is the formula. So now we need to calculate first of all XA value to use that formula. So XA can be calculated by B XA whole square divided by 2 is equal to MAST D minus XA. So what is B? It is 350. XA whole square by 2. M is equal to 9.33. I calculated the value of M so many times. And AST is equal to 3 into pi by 4 20 square D minus D is, so you can calculate D is equal to 600 minus 25 minus 10. It will be 565 minus XA. So you will get XA as 145.23. Clear? So I am substituting here sigma ST, that is for FE415 sigma ST is equal to 230. You need to remember this value. 230 into XA is equal to 145.23 divided by M is equal to 9.33 into D is 565 minus XA is 145.23. So you will get the stress is like 8.50 Newton per mm square. Clear? So the answer will be option B for question number 9. So the last question. A rectangular beam of width 350 mm and overall depth capital D is equal to 600 mm. The tensile reinforcement, so 3 bars of 20 mm, clear cover 25 and grade of concrete M30 and grade of steel FE415, moment of resistance. So that is moment of resistance. First of all, we need to classify whether the section is under reinforced or over reinforced before calculating moment of resistance. So B into XA square divided by 2 MAST D minus XA. So small d here 600 minus 25 minus 10, it will become 565 and M value is 9.33, that is B is equal to 350 into XA square divided by 2, M is 9.33 and AST will be 3 into pi by 4 20 square into D is equal to 565 minus XA. So that XA is equal to 145.23 mm. Okay, and XC is equal to 0.289 D, that is 0.289 D is equal to 565. It will be 163.285 mm. So here we got XA less than XC. This is under reinforced section. To calculate for under reinforced section, moment of resistance is equal to B into XA into sigma CBC by 2 D minus XA by 3. So that is B is 350, XA is equal to 145.23 into sigma CBC is 10, that is 1/3 of grade of concrete. For M30 sigma CBC is 10 and it will be 2, and D value we got it is 565 minus 145.23 divided by 2. So you will get the moment as 133 something into 10 power 6. So you will get it is 133 kilonewton meter. Okay, yeah. So now these are all working stress method. Generally nowadays the usage is limit state method. There are only some older constructions like bridges and water tanks. Working stress method is still they are using, but for modern constructions and beams like beams and buildings, so they are not using working stress method. So I hope the course is design of reinforced concrete bridges, so it is related to bridge. So the code is, the design is only by working stress method, so that's why you need to solve all this. But working stress method is not that important for GATE, but you need to know what is the difference between working stress method and limit state method. Okay, so what is the difference between if we design a beam by working stress method and limit state method? Generally by working stress method we will get larger dimensions, and in the limit state method we will get smaller dimensions. When larger dimensions are provided with smaller dimensions, obviously there is a saving of the material. Okay, so as the course is related to bridges, they are explaining all this content related to working stress method. Okay, so this is all the solutions for assignment number 2. In the next session we will meet with assignment number 3. If you have any doubt, post your comment. If you want any other courses, post your comment below. Thank you.